that you're going to have on Monday. So let me go straight away. Here, where are my slides? Share. Okay, so last time we saw lecture 9, which by the way is going to be part of the midterm, and then lecture 10, which instead is not going to be part of the midterm, of this midterm, is going to be in the next one. So now we need to finish for this week to see lecture 11. So lecture 11 is about 2D cinematics. And so here we saw already how to write the instantaneous position, RDT as X and Y component. Also the velocity is going to have 2 components, Vx and Vy. And the acceleration, you're going to have 2 components, Ax and Ay. Again, the magnitude of a vector is always positive and is indicated in this way. So you have, for example, if the acceleration is constant, the velocity is equal to V naught, which is the initial velocity, plus AT, while the position RT versus time is equal to the initial position plus V naught T plus 1/2 AT squared. So those equations are exactly the same equations that you saw in our previous classes. Now, the only difference is that we are speaking about vectors. So you are going to have components along X and components along Y. So let's discuss, for example, of the projectile motion. We saw last time when we were, or maybe a couple of classes ago, when we were throwing up a ball up in the air, up in the sky. So here we want to see the motion of a projectile, so that he has something in the vertical, he has a vertical component, but he also has an horizontal component. So the vertical, let me start first with the vertical components. The vertical components are exactly, and maybe if I do like this, it's easier to understand. So the vertical components are exactly the same equations that we saw when you throw up a ball, remember, in our one-dimension motion. So you have that V is equal to V naught plus AT. A, we know that is what? Gravity, remember, that is always going in the direction towards our planet. So and this minus G. And the y-axis normally goes up. So here you have Vy, because all of this is going to be in the y direction. So Vy is equal to V naught y plus Ay multiplied by T. The displacement along y-axis is going to be y naught, which is, am I going to throw the ball from the ground or maybe from a very tall building? So this tells you from where you are throwing up the ball, and then plus V naught T, which is the initial velocity that you use it, plus 1/2 Ay T squared. Ay again is our gravity, because y-axis goes up and gravity goes down. This is going to be minus G, right? And then we also have an equation to find the velocity as a function of the acceleration and the displacement, in case you don't know the time. So we saw already all that. Now with the projectile motion, you have in addition an horizontal components. So V naught is not going to be, when you throw the ball, you are not going to throw it really only along Y. You are going to throw it along Y, but also along X. So in front of you, you see, with a certain angle. So V naught is not only the Vy component, and for the Vy motion, we know that these are the equation, but it has also an X component. For the X component, is going to be, so Vx is equal to V naught X plus the acceleration along X times T, and then X is equal to X naught plus V naught along xt plus 1/2 AT squared, and again, the component of Vx. So you see the equations are exactly the same. We only change X and Y, you know, so this is the only difference, but it's not the only difference. We also have another difference. While for the y direction, we know that we have gravity, so our planet pulling all the object towards it. For the x component, we do not have any acceleration. We just throw the ball with an initial velocity. So if you see the components of our acceleration, here we are going to have zeros minus g. So in the reality, these equations are going to be way simpler, because every time you see a along x, essentially you're going to have 0. So essentially we can, simplify these equations, and what you have in the horizontal components, you just have these simple equations, while in the vertical components, you have the one that we did it already a few classes ago. So remember again that now the velocity is a vector, so you are going to calculate Vx, and you are going to calculate Vy. And the same is for the displacement. It's going to have a long x and a long y. So keep in mind that all these are vectors. Then is again, like we saw last time, when you get at the top, so what are the important concepts to remember? So the initial velocity, remember, we studied already, because you have gravity pulling down. The more the object goes along the y-axis, so goes up in the sky, the velocity along y is going to decrease, because of course you have the acceleration, right? So the acceleration is decreasing your velocity. So when you get to the top, remember, at the maximum height that you can achieve, you had that the velocity was equal to 0. This time is going to be equal to 0 only the velocity along y, right? So we are speaking about the y-axis. So the velocity along y will be 0. But as you see here, the vector, you still have a velocity along x. Because indeed, what do you have along x? Along x, because we don't have any acceleration, remember, the velocity stays constant the entire time. So here, the velocity along x is never going to change during the entire time until this object crashes on the ground. Okay, so it stays the same. Here, so at the maximum height, you're going to have the velocity 0 along y, but the velocity is equal to Vx along x. And then going down, of course, you're going to have gravity that is going to increase your velocity of the object going down. And so you get here at the end, which you have the exact same velocity along y, but in the opposite direction, because now the velocity is going down. And the exact same velocity, even with the same sign, along x. Okay. So here we could do some examples, but let me go. So you can also, another important thing that you can calculate is the range. The range, so if you throw the ball from here, when is it going to touch the ground? This is a typical question that we see in our problems. And you can indicate, there is a way, I mean, you can calculate going through these equations, but we already did it for you. We don't show you all the calculation. We make your life easier. So the range is going to be equal to V0 square sinus of 2 times theta. So the initial angle we do, you are throwing the ball. And when we indicate the angle is always the trigonometric angle divided by G. Okay, so of course, as you see here, the more the angle, so for any achievable range R, there are 2 possible launching angles with theta 0 and 90 minus theta 0. Then in all these things, we are considering that there is not air resistance. So always that, yeah, the resistance is 0, so the acceleration is always constant. So the acceleration or is 0 all the time, or is minus G. But of course, if you have the resistance of the air, of course, the maximum height is reduced, and also the range, of course, will be reduced, right? This is understandable. So if we want to look some examples, let's see with the examples that I was showing to you last time. Let me see. So we could go to examples of projectile motion, or I could just go on with the example that we were covering and leave the one of the projectile motion at the end. I don't know what you think, Mike. Otherwise, I can go to this one just to show one example. Maybe I can show one example of, yeah, I could show one example. So okay. Here, okay. So here what we have, for example, we have a mountain climber that encounters a crevasse in a ice field. Sorry for my accent. I never know if it's a crevasse or crevasse. I'm not sure. The opposite side of the crevasse is 2.75 meters lower, and the horizontal gap is 4.10 meters. So you are essentially here. I'm essentially here, actually. I have this thing that is 2.75 meters lower, and I need to jump. And the space in the middle is, the gap in the middle is 4 times meters. So I know that in reality, I'm never going to make it, but let's imagine somebody more fit than me and taller than me. So what is the minimum speed V0 needed for the climber to cross the crevasse? So here we have, again, two components. One is along Y and one is along X. So the first thing you can do is essentially to write all the equations, okay? All the equations along X and along Y to see what you know about it. So we are looking for the minimum speed, V0. So we have that here, V0 is, you see, is only along X. So we don't have anything along Y. I'm not jumping up. I'm just going with the X component of V0. So the Y displacement, it has H, which is the Y0. Our Y0 is H. Then you would have the initial velocity along Y, but we said we don't have any velocity along Y, multiplied by T. So that component is 0. And then we have minus 1/2 GT squared, because we know that the acceleration is going down and GT squared. Okay. So this one, with this one, you can put this equal to 0, because you are essentially jumping along the X direction. So here you can put it equal to 0 and find the time. And the time, you find out that the time is the square root of 2h divided by g. Now we are looking for instead the velocity. So V0, to find it, I have to write the equation for the x-axis. And the x-axis is x equal V0 t, which means that V0 is equal to x divided by t. I substitute t with what I found it before. And if I substitute all the numbers, I'm going to have 5.48 meters per second, which is the initial velocity. Okay. Then, suppose the climber jumps at 6 meters per second. Where does he land? So in this case, it provides you an initial velocity of 6 meters per second. So you have that x is equal to V0 t. So we are always, even here, we are discussing about the position along x, not the position along y. So that's why we are only interested to this equation. X is equal to V0 t, and this time V0 is equal to 6 meters per second. So we substitute all the numbers and we find that it lands at 4.49 meters. And then the last question is, what is the speed on landing? So the speed on landing, of course, will have the X and the Y component, because this time is not only the velocity along, oh, sorry, I need to enlarge it. Is not only the component along X, but is also the component along Y. So what we have here is we need the velocity along X we know. We need to know, because it was given before, provided before, 6 meters per second square, we need to find the velocity along Y. So the velocity along Y is V naught Y, which is 0, because it goes only horizontally. Here you see V naught is along the X-axis. GT. So T we saw before, that is the square root of 2H divided by G. So if we plug these numbers here, we find that at the end is 7.35 meters per second, putting inside all the numbers and making all the calculation. So now we know Vx and Vy, and we know that the speed is like the module of the velocity. So it's going to be the square root of Vx to the square plus Vy to the square. And also here you can make all the calculations. So you see, with two motions, when the motion is in two dimension, is a bit more complicated, because you have to study the motion in X and you have to study the motion in Y. But if you write all the equations, you have all the time have all the information to solve the problem. Sometimes you see here, you don't find an exact number, and you might find just an expression for one of the variable that you need to plug in another, in the place of the variable, to find the final result. So this was a bit complicated, but I'm sure that in the homework there will be simpler cases. Then I could go on with some of the examples here before going to few of the typical questions that we put in the midterm, just to give you an example of what will be there. So for example, here, let's review another problem. We have a sailboat that has coordinate 130 meters and 205 meters. So this problem is more about vectors, to become more proficient with vectors. So the coordinate 130 meters, 205 meters. So what you do, you make your sketch and you make this dot, which represent the position of your sailboat at t equal to 0 seconds at the beginning. Then it says 2 minutes later, its position is 110, 218. So 110 is here, 218, a bit less than 220. Okay, we put it here. Very good. Here you see, we draw a vector that goes from the initial position to the final position. This vector is called displacement, indicated with delta R, and you want to put an arrow on the top of it. Okay, so it makes sense that we can call this one delta Y, and we can call this part here delta X, which are the component of your displacement. So here is asking, find the vector velocity, average velocity, and then find its module. Now we know that the average velocity, the vector, is the average velocity along X plus the average velocity along Y, right? Those are the components. And of course, we need to put X and Y because this is a vector. So are two different in two different directions. So we can calculate what is the average velocity along X as delta X over delta T. So 110 meters minus, which is the final position, minus 130 meters. This is delta X, right? Divided by our famous, how many? 2 minutes? Okay, 120 seconds. If you do the calculation, you find this is the component of the average velocity along the x-axis. Then I need to calculate to be able to find the average velocity vector components, the one along y. So this one is going to be delta y over delta t. So final position 218 minus initial position 205 divided by 120 seconds. So is equal to 0.108 meter per second. And again, we see that the equation, the dimension makes sense because we have meters at the top, seconds at the bottom, meter per second is a velocity. Okay, we're good to go. So when I write this vector, I write average velocity with the symbol of vector is equal to the component along x, and I indicate x with the hat. Or you remember, we can also use I and j, but here is, we prefer x and y. So x with the hat plus 0.108 meter per second, y with the hat. Now it says find also the module of this vector. To find the module, we know that is x component, the square root of x component to the square plus y component to the square. So here we make the calculations, of course, because you see, even if it's negative, because you have the square, this always gives you a positive value. So you always have the square root of a positive value, which you know how to do it. And this one gives you again meter per second, because here will be meter per second to the square, but then you have the square root. So again, dimensions make sense. If you want to find it's not required here, but if you want to find the angle, we know that is arctangent of the component along y divided by the component along x. And also this you find that is 147 degrees. So if you see here, indeed, we already knew that it would have been something bigger than 90 degrees because it's going in the second quadrant. And indeed is 147 degrees. Very good. Now, another quick example. A dragonfly is observed initially in this position, 2 meters along x and 3.5 meters along y. 3 seconds later, it's observed at this position, R2, which is minus 3 meters along x and plus 5.50 meters along y. So here you see, we didn't make the sketch, but if it helps you, you always can make the sketch. So again, make the drawing with the position, initial position, and with the final position. So what was the dragonfly average velocity during this time? So in this case, the average velocity is delta r divided by delta t, so r2 minus r1. And here is another way to show you how you can do it. So you put all the x component here, minus 3 is the final position, minus plus 2 initial position. This is what you're going to have along x, plus what you're going to have along y is final position minus initial position. This is along y, everything gets divided by the time, because we know from this equation, right? So if you divide one and the other one, you find out what are the average velocity of the dragonfly along x and along y. And so you identify univocally your vector. Okay, now we have a hummingbird that is flying in such a way that is initially moving vertically with a speed of 4.6 meters per second and accelerating horizontally at a constant rate of 11 meters per second square. Find the horizontal and vertical distance through which it moves in 0.55 seconds. So those are not typical, as you see. So we have this time the velocity that is only vertically. So your velocity is only along y, while the velocity along x is equal to 0, right? And then it says that it's accelerating horizontally at a constant rate. So we have an acceleration along x. And we do know that we also have an acceleration along y, although here is not considered. So it doesn't consider the gravity. Yeah, no, it doesn't consider gravity. So find the horizontal and vertical distance through which it moves in 0.55 seconds. So along x, we are going to have x naught, which is 0. Speed, the velocity component along x is 0, so this goes away. So you only have 1/2 ax t to the square, and you have all the information. Along y, you have y naught, which is 0, v naught y t, which is provided because it's the 4.6 meter per second. And then we don't have any acceleration. It doesn't mention any acceleration along y. So we have only v naught y t. That gives you this result. So those are some examples to make you to become more and more familiar with this type of problems. Let me see the time. We can do this later. Maybe we can do first some of the questions. What do you think, Mike? Some of the questions for the midterms.
Yes, and I can also tell everyone that there's a sample set of about 12 or 13 sample midterm questions that are now available in Laulima, and you can try them multiple times. In fact, Veronica, would it be okay if I did a little screen share and showed everyone what it looks like?
Yes, okay. I'm happy to do that. So I switch off here.
Okay.
I don't want to share anymore. Yes.
Okay, everybody. So I'm logged in as a sample student to our Physics 151 account. And as you can see over, if you were to pull this up right now, you would see midterm number 1 sample questions. Okay. Now, unlike your actual midterm, if you open this one up, this one is too short. Okay. So it's shorter than your actual midterm, and it can be submitted multiple times. And immediately after you submit, it'll tell you whether, what the correct answers are to each question. Okay. So your actual midterm won't do that, right? You can submit your actual midterm only once, and you won't get the correct answers until a day later. All right, so if you want, you can practice these multiple times. All right, now I went ahead and repeated the sort of actual exam conditions that you'll see when you open up the midterm on Monday, just so you have this in front of you. You can preview it in advance. And this is pretty much repeated from the email announcement that went out yesterday. All right, so if you start it, if you've never taken one of these timed exams in Laulima before, then first of all, there's a countdown clock right there, okay? And you can sort of hide the time if it's bothering you, or if it's covering your table of contents tab, right? So you can either expose it or hide it, right? Please keep track of this, right? You will have 50 minutes max from the time that you start your test. Or if you start your test too late, your test will close at 10:30 a.m., even if your 50 minutes aren't up yet. And as you can see, then there's some questions here. I went ahead and your test will also have the questions divided into multiple pages like this, only there will be more questions, that's all. Okay, and we divide them into multiple pages for a couple of reasons, but the main reason is Laulima just behaves a lot better if we chop the questions up into multiple pages. I recommend that you use your table of contents tab to navigate back and forth. So unlike your problem sets, table of contents will not tell you whether you have the answer right or not. It'll just tell you whether you've answered the question. So it'll put a black dot on the ones that you've actually answered, right? So if I actually submit answers to these, then I go back to my table of contents, okay? So it shows me, okay, I've entered answers for those 3 questions, but notice how it's not telling me whether the answers are correct or not, okay? Like it does, like we have that turned on, that feature turned on for your problem sets, but it won't be on for your midterm. Right? And then after I submit, then when I look in my table and when I look again in my tests and quizzes zone, looks like, oh, great, I got a score of 0 that time. This was my previous attempt, was a score of 1.5. All right. So and then you can try it again if you want. Okay. So this one is just for practice. All right. So I think that Veronica and I are going to, here, if we take a look at this one, Veronica and I are going to model solutions for a couple of these. Is that right? Or at least I can do it.
Yes. Yes.
This will be, they'll be for the ones here on the last page, the jet airplane and the seabird. Okay. So here's the jet airplane right here. And there's the seabird right there. Okay. These last two. When you open this up, your actual numerical values are going to be shuffled and randomized a little bit from the ones that we're going to use right now. Right. So,
yes. So don't copy with each other because all these numbers are going to be randomized. Otherwise,
exactly right.
Otherwise we know, you know.
Okay. In that case, Veronica, what's the best way to do this? Veronica, do you happen to have just a graphic of
Yes.
the jet airplane problem? Then maybe I could try and write on the side of it if there's enough room.
Okay.
And if there's not enough room,
Well,
then I'll
there
put
is
up.
not that much room. Let me share another one so I can make more room for you. Give me 1 second. So if I share this new slide, I can just put these two problems into different slides.
Someone asked if the practice exam questions will be randomized every time they retake it.
Only the numerical values.
Yeah.
Yeah. Some, and only on some, right?
Okay. So before I
Great.
go there,
Hmm.
for example, just to give you an idea, here you're going to have 0.5 points, 1 point. So for each question, you will know how much this value. And then, for example, true or false, the base unit for distance in MKS system is the kilometer, true or false. So those are very simple, or otherwise you will have multiple question, multiple answer. Which of the following are base fundamental physical quantities of the SI system? Select all that apply. And then other times instead, you will have something where you need to make the calculation. And yeah, Mike, here,
good.
you should
That's
have
actually
enough
perfect.
space to.
Yeah, that looks good. There's plenty of space there.
Yeah.
Okay, good. Okay. All right, everyone. Well, in that case, I can use some of this time now to sort of model how I would solve this problem. Okay.
Yes.
So everyone, what I want to remind everyone about is the sort of main steps for solving kinematics problems that were talked about in lecture number 6. So actually, Veronica, if you don't mind, I'm going to briefly interrupt your screen sharing just to put something up.
Yeah, sure.
And maybe you can re-screen share in a second. So everyone, so I've just copied this out of the lecture number 6 slides. And all I did was remove some of the words and make the 6 main steps. I colored them rainbow colors. Okay, so that's it. But otherwise, this is in lecture 6. And I want to remind everyone, okay, whenever I face any of these kinematics problems, or really the upcoming dynamics problems, any physics problems in general, then the first thing I do is I try to visualize the situation. So I imagine as much as possible sort of what's happening here. Okay. And if I'm given like a graph or just a bunch of numbers, I try and put it into a physical context. And that will help me to understand what will be sort of a reasonable answer down here at the end, if I really sort of get what's happening. It'll also help me to choose what directions to use for my axes. I want to simplify my math. I want to choose axes that are going to be along the motion of the object as much as possible. Okay, so there's going to be traditional ways that we always choose our axes to just do that, to make the math simple and sensible. Then, in combination with step 2 and step 3, we think about what is the desired unknown thing I'm trying to solve for. Is the problem asking for the time or the distance or what? And then in the word problem, you're always going to be given a bunch of other known quantities or given quantities as well. So try to identify what these are, and as much as possible, tie them to our traditional variables. Am I being told V? Am I being asked for time? Am I being told V naught? Things like that. Right? Then I look at my kinematics equations for constant acceleration, or, we've actually learned a few other equations too, like equations for average velocity and things like that. I open my toolbox and look at all the equations that I've collected up to this point in the semester. And you're going to continue to get many, many more equations in the coming weeks. And I look for maybe, if possible, a single equation that contains the unknown I'm looking for. And then the rest of the things in that equation are known. And if I find one equation that will do all that for me, then use it, right? I use it. I set it up, plug the known values in, and I solve for the unknown. Now, on exam problems, it'll be rare that you'll need multiple equations. On homework, longer homework problems, that'll be more common. But you may need to use 2 or more equations that's in succession to get to your final unknown quantity. But in Physics 151, that's less commonly the case, right? It's more commonly the case for Phys 170 or more advanced courses. So usually a single equation will be, most of the time, all you need. And then once I've done that, then all that's left to do is some math. So then you solve for the unknown, and then make sure you sanity check your final answer for reasonableness, right? And as you solve, I watch all the units try and cancel as much as possible to see what sort of units I'm left with on my final answer. Okay, and make sure and that's part of my final sanity check at the end. All right. I'm going to try and model for you. I won't call them by steps number 2, 3, 4, but this in my mind is what I'm going through as I try to solve any of these problems. So Veronica, could I ask you to re-share your problem screen? All right, great, thanks. All right, everyone. So we have a fighter jet airplane that accelerates horizontally from some initial speed to some final speed. And we're given the acceleration. Although look at the units. The units here are in G's, which is kind of an odd unit. Let me see. Can you all, looks like I'm not actually drawing on your screen. You can't see my writing, correct? No?
Correct.
Okay. All right. Well, all right, let's just sort of look at the problem, and then I'll put up a plain whiteboard. Let me see here. Yeah, I don't know why it's not annotating correctly. Okay.
So you cannot write on that?
Yeah. Oh, now it's working.
Ah,
Okay, good.
okay, now it's
great. I don't know why it didn't work initially, but all right, so now it's working. All right, let me start over. So when we look at the top of the problem, it looks like I have a fighter jet that's starting at some slower speed, increasing to some faster speed. This is along a straight line. Okay, so it's a one-dimensional problem. And I'm given the acceleration over here, but notice the units are funny. The units are in G's. Okay, and what am I being asked for? I'm being asked for the distance that the jet travels during this time period as it goes from some initial speed to some final speed. Okay, all right. So if I wanted to, I could actually draw a little sketch. I don't know how to draw a plane, right? You can just draw a box or a blob or whatever, it doesn't matter. There's some initial velocity, and then sometime later, there's some much faster final velocity, right? And we're told that there's an acceleration that occurs during that time period. But ultimately, what we're being asked for is what is the displacement, right, or distance traveled of the object. So we're going to want to find that delta x. So this is our desired unknown. Notice that time is neither given or asked for. So if I can avoid an equation with time, that'll save me a little bit of effort. All right, so if I look now in my toolbox of kinematics equations, is there a kinematics equation that I can choose that uses the known quantities and allows me to solve for the unknown quantity? And I'll pause here for a sec and let you think about that. And I have one in mind right now. Out of our 4 equations of kinematics with constant acceleration, let's see if you're thinking of. Great. And known, oops, known, oops, what happened to my annotation? Known, unknown. Perfect. So now I can solve. So I'm going to plug in the things I know. 347 meters per second squared. Notice how I'm going to carry all my units in the calculation, which is good practice. And that way I can watch them cancel as needed. Now the acceleration, unfortunately, is given in odd units. So I need to convert this. 2.63 Gs. And remember how a G is 9.8 meters per second squared. Okay. So that is 25.774 meters per second squared. Now notice I'm carrying extra sig figs, right? I was given 3 sig figs for the acceleration, but you should probably carry at least 4 for these intermediate values to prevent round off errors. So I would carry at least 1 extra sig fig on the acceleration. If it's on your calculator screen, just carry everything, just leave it there and just keep using it. And then I solve for the final displacement and I get 1024 meters. Okay. And the final answer is being asked for in kilometers. So I'm just going to convert that to kilometers, 1.024 kilometers. Now, if this were a real life problem I was going to hand in, I would say, okay, it's a 3 sig fig problem. So I'd round to 1.02 and turn that in as my final answer. But Laulima don't give a damn about significant figures, right? So you can just put in as many sig figs as you want. Don't put in too few. Otherwise, Laulima will think your answer is rounded off incorrectly. That is too far off from the correct answer, right? And it'll count it as wrong. But otherwise, you can put in as many as you wish and it won't count it as wrong. And I want to draw your attention to the fact that on most of these exam problems, I have a hint. So there's a big fat hint right there. So is my answer within the hint range? Yes, great. So I would go ahead and type that into the box, click, and then move on to the next problem. And remember, during your midterm, you can't check to see if the answers are right or not, okay? So you just got to use the hint that you're given to see if it's in that sort of range of expected answers. Any questions about this one before we go on to the next and last problem? I recommend that you do this work on an actual sheet of paper on the side, right? And that you not just try and put it in your calculator screen or just put it in whatever you're using to do your numerical calculations, right? Wolfram Alpha, Desmos, whatever. I recommend you actually write it out, allow you to double check it later if you want to find out like what might have gone wrong or what went wrong. And it'll allow you to review it later when you study for the final exam. Yep. And you'll just make fewer calculational errors, right? When you write out more steps on the page. That's my general advice. All right. Well, let me try and clear my screen here. Okay. And Veronica, could you screen share or move on to the last problem? I think there's one about a seabird. It's just a vector question. Great. All right, thanks. All right, everyone. So same thing. Initially, read the problem, try and visualize what's happening. So there's a seabird flying over the ocean, and we're viewing it from high above, okay? So sort of a bird's eye view from even further above the bird, okay, looking down on the bird below. The bird is flying at a trig direction of 233 degrees. Okay, so not a compass bearing here. That's a trig direction. And the x component of the bird's velocity is negative 2.23 meters per second. And you're asked to find the y component of the bird's velocity. All right. So if I were to sort of sketch out or visualize what's going on here, now, unfortunately, it doesn't actually say it here, but what I will normally say is I will also say in the problem that the positive y direction is equal to north and the positive x direction is equal to east. So when you look down from high above, right, high above the bird, where is a trig angle of 233 degrees? I'll let you think about that for a sec. What direction does that point? I hope you agree with me that it's somewhere in the southwest quadrant or third quadrant of these axes, correct? So it's down there. So the vector that we're talking about, the velocity vector, looks like this. That's the bird's velocity vector as viewed from high above. All right. Now, we're told that the x component is negative 2.23 meters per second, right? So that means that the x component here, Vx, sorry to write stuff backward like this, 2.23 meters per second. And we're asked, what is the y component? Okay. So we have the trig angle and we have the x component, and we're asked to find the y component. All right. So I could think of a couple of different ways to approach this. Let me give you a moment to think. Which of our equations for decomposing vectors to find the missing y component, given the things that we're told? All right, so one approach I could think of is to say, hey, we know that the tangent of the trig direction is equal to the y component over the x component for any vector. So if I think about my knowns and unknowns, we're given the x component, we're given the trig direction, and we're asked to find the y component. So I think that means I can just do one-stop shopping with this. So the y component is going to be equal to the x component over tangent of trig direction. And I asked my calculator what that is. Oops, I don't know what just happened there. Sorry, I had some sort of a screen glitch. Okay. Let me just try and finish this here. And I asked my calculator, what is that? And my calculator tells me that the y component is negative 2.959 meters per second. So if I'm going to hand this in for written homework, I'd say 2.96 meters per second, because it looks like it's about a 3 sig fig problem. Okay. Again, Balima won't care. Okay. If you put in too many sig figs. And then let's sanity check this answer. Does that look about correct? Good. Yes, that looks reasonable, right? It looks like negative 2.96, right? Definitely the correct sign, definitely about the right size of quantity. All right, good. Now there's other multiple correct ways to approach this, right? Another way you could do this is you could say, all right, I'm given the x component in the trig angle. I can use that to get the magnitude. So another way to approach this would be I can get the magnitude using Vx is equal to V times cosine of the trig angle, solve for the magnitude, and then separately, in a second step, solve for the y component, right? So that would be two-stop shopping, right? First, you use this initial equation and then the second equation. Also a correct method, right? Using this tangent equation down here was just one-stop shopping. That's the only difference. Ultimately gets to the same answer. Okay. Asher Ganoza asked, is this lecture 9? No, this is lecture, well, yes, close. It's lecture 8. Lectures 8 and 9 are vectors and vector math. Yep. Other questions about this problem? Looks like, I'm sorry, Veronica, looks like the time is almost up. Okay. Now this one doesn't have sure that if your answer is negative, be sure to enter a negative value, but that's all for that. Okay, I'm going to try and, oh, it's Veronica that's screen sharing. Okay, so go ahead and stop your screen sharing, and I guess we could end.
Okay, I think it was really good. So it gives to the students a possibility to see some of the problems. Yes.
And when if students open the same problem in the sort of sample midterm questions, they'll get the same question, but the numerical values will be a little bit different. So
yeah,
they can sort of try it.
Work again. Okay, so good luck, everyone. Have a wonderful weekend and good luck on Monday for the students. Bye-bye.
Oh, everyone, I'll stick around a few minutes. And I think Julia, do you have office hours here coming up? Okay, great.
So Mike, do you want me to stay or I can leave?
I think you can leave. I think that's all right.
Sounds good.
Yeah.
Okay. Sounds good. Bye-bye, everyone. Ciao.